I'm going to go over a couple of the ideas from multiple comparison procedures from our textbook being Lomax and House-Vaughn's textbook for statistical concepts, but just this in general too. It's still useful for somebody that's stopping by, it's not in the class. So this is for our analysis of variance series. So I'm going to discuss a couple issues around contrast, comparisons, both planned and post hoc, and simple and complex multiple comparison procedures. But really, this is just as a refresher for some of the stuff that you've read or we've done in class or from other videos. So let's go ahead and get started. We have an analysis of variance. We reject it. That means that we reject the null hypothesis. We say that the null hypothesis is false, that indeed there is something else going on. Well, what's going on? Where is there a difference in our data? If we have two groups, if we have two means, it's really easy. The difference between those two means is what made the significance occur. But anytime we have greater than two groups, we need some sort of method of comparison. We could do t-tests, right? We could do lots and lots of t-tests. But some of the issues are that we're going to have some uncontrolled type 1 error rates, and I'll show you what that means in a moment. Should note that multiple comparison procedures are appropriate for our fixed factor effects, not our random effects models. When we talk more about random effects, or if you already know about them, that's great. Random effects models are going to be that when the F value is significant, it sort of shows you that for the entire underlying concept that you sampled for. Here we fixed these values. It means we chose them. Random effects means that we randomly selected those effects from a population. Like you might randomly select people from a population, you could also randomly select levels of a factor from a population. For this model, we're just assuming these were fixed values. We chose them, we thought they were meaningful or important, or maybe available. Some situations we may not be interested even in the overall F-test, so we go right to the multiple comparison procedures. What is a contrast? It's a weighted combination of means. And as you can see here, maybe I'll come off this slide projector like this. As you can see here, this is our equation, which is really saying some proportion of group 1 plus some proportion of group 2, etc. In a really simple comparison, what we have is something like we have three groups. We're going to take all of group 1 minus all of group 2, so we code it that way. So we end up with group 1 minus group 2. A more complex comparison would be like if we want to compare group 1 to a combination of groups 2 and 3. Basically, it's like group 1, and then if you had this new supergroup that was an average of groups 2 and group 3, that'd be a more complex comparison. So really, it's just a fancy way of talking about coding for when I will want to look at a direct comparison, because I have this idea that I should be comparing group 1 and group 3, or maybe group 2 and group 3, and those are specific focuses I'm interested in. For multiple comparison procedures, we can do the standard T. This is a little bit different than the t-test we're accustomed to, although very, very similar in theory. We're going to look at some sort of contrast or difference between means, right? In the numerator, that's the difference between means. And the denominator, some form of standard error. We're going to base it on the mean squared error that we pull from our test for analysis of variance. So it's sort of like a super denominator, a super standard error, or super standard deviation, right? Because it has more information than just what's in the two groups that we might be comparing. One more thing before I show you some practical comparisons I'll set up in Excel is that these things can get crazy and out of hand. So what I mean is, just with 5 groups, just direct comparisons, we have j times j minus 1 divided by 2, which is basically 5 times 4 divided by 2, which equals 10. That doesn't seem like that big a deal. Maybe that's okay. We can compare 10 groups. However, we run into a problem for type 1 error. And that problem in type 1 error is that it's not just like we have 0.05% chance of finding a difference when one doesn't really exist. That is, it's just due to chance alone. We now have this cumulative chance, and here's our little equation for that. So when we look at experimental wise error, we have 1 minus parenthesis 1 minus alpha and parenthesis to the power of c. C being the number of comparisons we're going to make. So let's break that down. Let's stop for a second and let's break that down in Excel. So I'll get back to this. This is going to be a descriptive data example we're going to use. It's the same descriptive data example we've used in chapter 1 and throughout the course. So this is just the outcome from SPSS. But I'm going to just give you a quick equation. So we're going to say if we have, as our example was before, 5 groups. We're going to go ahead and put that in here and say we have 5 groups, so we have J, which is 5, times J minus 1, which is 4. Divide that whole thing by 2. We get 10. Now, we could also say we have more groups, right? It's not impossible. Analysis fair in this group, in this comparison, we had less. We had 4 groups times 4 minus 1 is 3 divided by 2. So we ended up with 6 possible comparisons. What if we had 8 groups? You know, think about analysis of variance. You have 8 groups you selected. The number of possibilities are 8, which is J, times 7, J minus 1, number of groups minus 1, divided by 2. We now have 28 possibilities. All right, so what does that mean for alpha? Remember, we have a 0.05. We're going to set it at 0.05. We say, well, alpha equals 0.05. We're willing to accept when we reject the null that 5% of the times we shouldn't have. Or another way of thinking about this is our margin of error. It's a reasonable margin of error that we say, well, even though we have strong evidence to suggest that we should reject the null, there's always a chance we were wrong. So let's go ahead and plug this into our other equation here. The other equation we looked at is our type 1 error rates. For one group, we can go ahead and plug that in. Let's go ahead and write this equation out. We have 1 minus alpha to the power of c. So first, let's just say for one group, if we have 1 minus 0.05, that's our alpha, to the power of, this is the power of in Excel, 1, if there's just one group, we end up with 0.05. We still control type 1 error rate is still, overall error that we're going to make by doing all of those models, which in this case is just 1, is still 0.05. Well, let's try that for 10. All I'm doing in here is going into our equation. We have 1 minus 1 in parentheses minus 1 minus 0.05 to the power of 1. Instead, let's make it to the power of 10 because we have 10 possible contrasts. That now changes. If we do a t-test for 10 groups, 10 possible comparisons, there is a 40% chance that one of those tests was due to it is significant just by chance alone. And we can see if we have 8 groups that we're comparing, we ended up with 28 possible comparisons. We can see that if we do all possible comparisons with the t-value, that there's a 76% chance that one of those are just due to chance alone. That is, we found significance amongst these comparisons just based on random chance, which is what we expect sometimes. Sometimes these things just occur. Hopefully that was a little helpful, that example. Let's go back. We have our number of comparisons. Planned comparisons are those things we want to do. We decide a priori. Before we even run an F, what do we want to study? You know, sometimes we know what we want to study. It's not even truly the F value. We just want to study 3 or 4 of the comparisons. So we might have 28 comparisons with 8 different groups, but there might be very specific focused comparisons we want to make. We can control for error by controlling the number of tests that we do. Other times we have the analysis of variance. We just want to test every possible comparison. We didn't plan ahead of time. We can look to see which patterns are significant. There's ways to control for this. We can compare several means, as I meant, family of groups to compare. You have all sorts of means in your data set. So we could look at all 28, but we need to find in the example where we have 8 groups. We need to make sure we control for this and control for what we call family-wise error rate, which is the error across all models, which is what we looked at when we looked at this equation here for controlling our alpha for a set of comparisons. We're controlling our overall chance of finding something, a chance of finding something different when it was just due to chance alone. So in this example, we set it to 0.05, our family-wise error. There's error with 2 R's. Let's go ahead and change that. So we have 0.05. We could set it to 0.01 as well. That makes our overall omnibus error rate a little bit lower. I sort of already showed this, and we'll do this again in class. Orthogonal contrasts are those contrasts that are independent and non-redundant. All contrast coefficients should total to 0. This is just a method of contrast coding. So we can see here that, for example, if we have 3 groups, we only have 2 contrasts because the total number of orthogonal contrasts, of non-overlapping, independent contrasts, is only going to be J, number of groups, minus 1. So here we can observe that if we say C1 is group 1 minus C2, that's one group we're going to look at. That comparison, and the second one would be, we can take a portion or half of C1 and half of C2 and compare that to group 3. We can go down here and we can multiply plus 1 by plus 1/2 and get plus 1/2. We can go down minus 1 times plus 1/2 and get, actually that should be a minus 1/2. And we can take 0 times minus 1 and get 0, and you can sum across and see that ends up summing to 0. That is a way to check to see if you have orthogonal contrasts. The back of your textbook also has some of the preset orthogonal contrasts. Trends are basically orthogonal polynomials. They're like our contrasts, except we're looking for some specific types of trends. Here we want to see a linear trend, so we can see, although we have 3's and 1's in this example, we can see we're going from minus 3 to minus 1 to plus 1 to plus 3. In our quadratic trend, there's a bend in here. We're going from plus to minus to minus to plus. There's one bend in that. For our cubic trend, we're going from minus to plus to minus to plus. There's 2 bends in that equation. So we have a linear trend, a quadratic trend, and a cubic trend. This is just one example of how to code for that. And we'll do more in class. I'm just coming back quickly to the standard T. This is a multiple comparison procedure test we're going to create. It's just like our regular T. I want to come back to this. We can see the numerator again is our group, and the denominator is a standard error. I'm going to come here and do a little practical example. I sort of already worked it out, but I'm going to come back to it and do it again for you. So let's do the denominator first. I said the denominator is based on the mean squared error and some sort of sum of our contrasts. Those contrasts are the things that we want to compare to each other. So you could be comparing group 1 to group 3 or whatever else it might be, maybe a more complex comparison. Well, when we ran our analysis of variance, we ended up having our mean square error. We can see our mean squared error is 36. All I did is put that over here. That's our MSE. So for the equation here, we'd be plugging in mean squared error of 36. And here it is right here. Now that contrast code, I am taking, and I want to say, well, let's sum all of those codes divided by n. Well, all that we're doing is taking the things we're interested in this case, we're interested in comparing 2 groups, both of them as a denominator of number of n in each group. So n is 8, n is 8. We're taking 1 divided by 8, adding those 2 things together, and we're going to multiply it by the mean squared error. We're basically taking the sum of those 2 values, the contrast we're interested in squared, 1 squared is still 1, divided by n, which is 8. We do that for both groups, and we multiply that by our mean squared error, and we're going to take this standard deviation of that. So when I do that for just the error for the denominator, we end up with, within the standard deviation, of a value of approximately 9, We then take the square root of that, and we get a value of 3. If you check on page 63 of your textbook, you'll see the calculation done out by hand for you, where we take 36 times 1 over, times in parentheses 1 over 8 plus 1 over 8, taking the square root of that whole thing, and you get 3. That's our denominator. That's the denominator we're going to use when we compare group 1 to group 2. Guess what the numerator is? It's group 1 minus group 2. You could do it the other way around. In this case, I took group 1 minus group 2. 11 minus 17, I got approximately 6.75, or I got exactly 6.75. So that's my numerator. My numerator is a negative 6.75. And my denominator is approximately 3, and I get a negative 2.25. Here's a more precise value. If you go look up in your book on page 63, this will help you out with that example as well. And we can do this for every single one of those examples. You can do this for on page 63 and for all of those comparisons. I'm going to go ahead and stop here. This video is kind of long enough. This is just kind of our intro to multiple comparisons, and given later on I will both be teaching some more of this in class, but so you have this to come back to as a reference, and also I'll probably be adding more of another video.